the chat window too. Okay, so what I'm going to do in this 45 minutes is to go over and finish these slides quickly and then show how we do it in this example program. Okay. Oh, a very good question. gluPerspective does not load a new matrix. It just creates a perspective matrix and it multiplies that created perspective matrix with the current projection matrix. So all of these function calls that about matrices, the only one that resets everything is this glLoad identity. Okay, so glLoad identity has resets the matrix to the identity matrix. So, or you can, there are also function calls that have you can change the matrix contents directly. For example, I think there's glLoad matrix function call in which you can change the matrix content directly, but the gluPerspective function call does not do that. It doesn't load the matrix. It multiplies the current matrix. So therefore, we have to call glLoad identity before we call gluPerspective. So one error you can do is if you successively call gluPerspective function calls in your code, it will change everything. So it will multiply, it always multiply the current matrix, and it right multiplies. Just like as we are composing matrices, whatever the current matrix is, it's right multiplied. So from your perspective, so this is the right part, right? So if you look at the camera, if this is the current matrix, the new matrix is put on the right, and it's multiplied that way. All right, so it's just like the order of matrix multiplications from left to right is what you see in your code. And this not only applies to the perspective matrix function calls. There are, for example, you can be in glProjection, and you may call, for example, glTranslate or glRotate. What does glTranslate, glRotate? The three basic transformation function calls that we use in OpenGL are glRotate, glTranslate, and glScale. And they all come with some, for example, we can have glRotate 3F, glRotate 3I. So the function calls in OpenGL come this format. I think glRotate or just glRotatef, because it just contain, let me see how glRotate is. Sometimes the number of parameters of these functions may be changing. I think it's just glRotate. Or maybe I don't have that glRotate here. glScale. Yeah. So glScale, for example, always gets 3 parameters: the SX, SY, and SZ, the scale parameters, and it always gets 3 parameters. So therefore, this F here tells we are supplying floating point numbers. Okay. I think there's also glScale D, or I mean, this letter at the end specifies the type of variables you're supplying. For example, here glLightFV specifies that you're going to be specifying giving floating point numbers for your glLight parameter, and the parameters are going to be in vector form. This is what this this V is about, and we are giving the position in vector format means that we are giving an array. There is glScaleF, and also this is the format of function calls that I want to mention. For example, just glVertexnt, it comes with 3 values after that. The number, for example, glVertexnt NT type of thing. This N is for the number of parameters you are going to be given. For example, there's a version of glVertexnt with 2 parameters. If you're doing 2-dimensional computer graphics, you may want to supply only X and Y coordinates, and there is a version of this glVertexnt function call with glVertexnt 2. And if you specify integer coordinates, you can say glVertex3i. And actually, these are integers here. I could have called glVertex3i. Probably when I say glVertex3f, all these are automatically converted to float during that. The function that is responsible for that gets them as floating point numbers. Yeah, so whenever we call a function like glTranslateF, what it does is it creates a translation matrix, which is 100 minus 200, 010, 200, 0010, and 0001. So it creates a 4x4 matrix, and it multiplies the current model view matrix, whatever the current, it depends on, for example, what the current matrix mode is. If your current matrix mode is still projection, it will actually multiply. It's possible to multiply your projection matrix with this translation matrix. It may do something really weird things to your projection. But what it does is it creates this translation matrix, and it right multiplies your matrix with the current model view matrix, because the current state is the model view state. And this push matrix, we're going to see what this push matrix does. It copies the current matrix. It creates a copy of it and puts this on a stack. We have a stack of matrices for the current model view matrix. We use this, for example, if you want to apply this translation only to, for example, you want to draw quads with this. I think this is like the color is this purple, the purple small rectangle in front of the table, the lamp. That small rectangle at the top. So this one, this is what I'm talking about. You see this purplish thing right in front of it? This purple thing is drawn here, and it's actually its position, as you can see, its y coordinate is 0. So if you look at the vertex coordinate values, this is not the actual coordinate values we see. This is like centered at origin. So if I just remove this translation, you're going to understand what I mean. Actually, you probably, something simple you probably understood. So actually, it's so the origin actually I think is here. No, it's not the origin. It's y coordinate. So y0 I think is here, or maybe did I have any other transformations here? No, I do some scaling. So I multiply everything by 10. But its y coordinates are all 0. It shouldn't be affected by that. So y is equal to 0, I think is somewhere here, or if I didn't scale anything before. So depending on whether I did any scaling before, I think I didn't do any scaling yet. So this is actually, it was moving it 200 units higher. So this is, as you can see, it's now at a lower position. Okay. Now, and it only affected whatever I do here. For example, if I have this glScale 111, instead of multiplying it with 10, I have a scale matrix which is just 111. Let me stop this program and compile and run it again. I just want to show you that now it's very small. Let me go near to that one. Yeah, you see this small quad here? It's 10 times smaller than the previous case, but only that one became smaller, not the other objects. The lamp is still the same size. This other rectangle is the same size. Only that one was affected by this glScale. But there is a single model view matrix. How can we make a certain transformation only affect a certain object? We do it like this. With this glPush matrix function call, we copy the current state of the matrix. Just at this point, whatever the model view matrix is, it's copied. We create a copy of it and we put it on top of the stack, the the copy is put on top of the stack, and there's another copy underneath it. And all these translatef, scaleF function calls, and the top of the matrix is always the current matrix. So whenever you do some glTranslateF, glScaleF, you actually multiply. Oh, by the way, this one, at this point, this translatef affected our light position too, I think. This push matrix here, this is the place where we only affect our, the purple quad that we have seen. But whatever here, gel push matrix copies the current state, and when we say scaleF, only the top of the matrix is affected. And when you draw your objects, after drawing your objects, if you call pop matrix function, what happens is that the top of the matrix is popped and deleted. So which means that the last matrix multiplication you have done, you undo that. You go back to the previous state. So glPop matrix basically is the same as saying that go to the previous state of the matrix. glPush matrix says that copy the current state, and now I'm going to make modifications on the current state. And when you say pop matrix, go back to the previous state. So it's just all the things that we do on matrices are in a hold on a stack like this. It allows you to apply your transformations in a hierarchical manner. For example, if you have a car model, you want to transform the entire car as it moves. So there is some transformation, you apply it as a whole. But sometimes if the driver moves from the left seat to the right seat, it moves along with the car, but there's a specific transformation which is applied on the driver separately. But it's something hierarchic, as you can imagine. As the car moves, the driver moves along with it. So I have to apply the car movement transformation should be applied both to the car model and the driver model. But the driver has an additional transformation too, which is moving to the right seat, for example. And after drawing the car and the driver, you may draw a house, for example, which is which has a different transformation. So you all this before drawing the car, before drawing the house, you should undo the transformations you applied on the driver and on the car. So the way to do that is to use this push matrix, pop matrix functionality. Okay, now let's quickly go over these slides. It describes certain methods to send this vertex data and draw them on the GPU. The first method is the most inefficient method in OpenGL, which were used the first time OpenGL standard was available to users. The way to do that is to send your vertices one by one with this function call. From the CPU side, in your OpenGL program, you say that to the OpenGL that I'm going to now be drawing lines. My primitives are going to be lines, and I'm sending the vertices, the endpoints. I think when I say lines, you have to specify 2 points at the end. It's like line segment, actually, not an infinite line. It draws line segments between 2 endpoints from x0, y0, z0 to x1, y1, z1. So this line segment is drawn between these 2 vertices. You can have, so let me, in my code, I'm going to show you something, which is this one. Look at this, GL triangles. I tell OpenGL that now I'm going to draw some triangles. And these triangles, they all have a normal vector of 0, 1, 0. They're all facing upwards. These are the triangles that make up the tabletop that the lamp is sitting on. And here I have how many triangles? So after GNOME 3F, I send my vertices. And if you look at these for loops, this is 300 times 301 actually. This is also 301. Multiply them with each other. 300 times 300, 9,000. Is it something like that? Yeah, I think it's or 90,000. Yeah, it's 90,000. So there are 90. This for loop runs. This one 300 times 300 times, so 300 times 300. It's 90,000 times. So at every frame, I make this 90,000 times this many function calls. So this is really inefficient, and I'm sending this vertex data at every frame. So that's the inefficient way of doing that. I have both of the efficient and inefficient way in this example program. I could have sent this vertex data, whatever vertex data I have here. As you can see, U is changing from -150 to 150. I could have put all of them into an array and send them with this glBufferData command to the GPU. But this inefficient way is also working. It draws the triangle. I think my initial idea was to use just two triangles. So when you look at this GL triangles, this function, these function calls that are commented out, let's get back them on. It draws the same thing, okay, with the same boundaries, but now the entire tabletop is drawn with two triangles. So the way these vertices are combined into triangles is done automatically by OpenGL. When you say my primitives are GL triangles, when you specify vertices like this, every consecutive three of them are combined together into a triangle. So this becomes a triangle, this becomes another triangle. So you draw two triangles with this glBegin triangles command. What happens if you have additional vertex calls at the end? For example, a seventh glVertex call at the end, it's ignored by the OpenGL program. So every three by three, it combines them together to draw a triangle. But as I said, this is the inefficient way of doing it because every time in the CPU side, this is a function call. An activation record is created, so it takes a long time on the CPU. This function is executed on the CPU, and then the data is sent to the GPU, and it's executed this many times. I think initially I just wanted to draw the entire table as just two triangles. If I'm going to have just two triangles, there is no need to send it as buffer data. But here, as you can see, it's a lot more triangles. Now, if I run and compile the program like this, something is not working, you're going to see. The spotlight, I'm turning it on and off, but I can't see the spotlight. So, is the spotlight functionality not working? I mentioned this bug before actually to you. What's going on here? I'm turning on the spotlight, but I don't see the spotlight here. Does anybody remember why this is the case? So there should be, this part should be, exactly. Thanks, Bugra. The color is interpolated because right now, the color that you see here, the vertices of these two triangles are the corners. So unless I move, let's try to move my lamp over to that side. So how do I move it left and right? So up and down. I should be able to move it left and right. Yeah, right this way. Which one? Yeah, this one. Let's try to move it here and move it a little bit forward. Maybe I should be able to see it. Turn it on. You see what happened? Right now, this corner, this vertex is affected by the spotlight. And when I turn on the spotlight, it doesn't look like a spotlight at all. And even this part is highlighted. Why? Because this vertex color is affected by the spotlight, and this vertex color affect this entire, both of the triangles are affected because this is incident to both of the triangles, it's affecting both of them. So if I move it, for example, over here, only this triangle is affected, right? Because this corner is a corner of this triangle, the other triangle is not affected at all. As you can see, this doesn't look like a spotlight at all, but although it is. Now, because the color, if you have very large triangles like this, it doesn't work. So how did I solve this problem in my code? I just removed these two triangles, and instead I drove the same table again, okay, but this time with lots of small triangles. Instead of this large triangle, let's have this the same area. Let's cover the same area. Let's comment it out again. Let's cover the entire area, this time with smaller triangles. This way, my spotlight effect is nicely seen. Okay, because there are like, I think this table contains also around 3,000 triangles on it. So there are 3,000 triangles here that you're seeing. So therefore the spotlight effect is nicely done. Or is it more than 3,000? So this is, I wrote this code myself 4 years ago, but I'm really puzzled on, this is glTriangles code. I have these for loops. How did I make the entire grid as triangles when I specify, oh, okay, it's very simple, sorry. So so this is a triangle, this is another triangle, right? This is like, every grid cell is like it's a quad, which is composed of 2 triangles, okay? So, so there are 2 triangles multiplied by 90,000. So there are 180,000 triangles on the table now. So, okay, so those 2 triangles that were very large are replaced by 90,000. 2 triangles here. Yeah, 180,000 triangles. It's very inefficient. Okay, so this is the inefficient way to send geometry data. And when we change the color, for example, when we apply the color is also something, a global variable. We can assign different colors to vertices. When we call this color function, we are changing the current color to that. And whatever vertex we have after that, that color is automatically assigned to this vertex. Okay, so we can send geometry data like this. With 3 vertices, we can define triangles. We can draw triangles like this. And when we are, there are different primitive types. For example, I could have used the triangle strip method instead of duplicating these 2 vertices at the ends of the triangle. Actually, this is exactly what I'm doing, right? Some of the vertices are duplicated. Look at this. U0, V plus 1. U0, V plus 1. These are the exact same vertex coordinates. The 4th one and the 1st one are the same. Also, U plus 1, 0, V. U plus 1, 0, V. So 2 of the function calls are unnecessary because I'm sending the same vertex data twice. If you're going to have a grid of triangles like this, a strip of triangles, there's a primitive in OpenGL for that, triangle strip, which will, what it will do is it will take the first 3 as your first triangle, and the 3rd vertex, I mean these two vertices will be shared, and the 3rd vertex is going to define the 2nd triangle. So you can have a strip of triangles, and therefore if you want to have m triangles, you only need m plus 2 vertex call, not m times 3. Instead of using GL triangle strip, if you use GL triangles, you would require 3 times m vertex call for m triangles. But still, all these are really old school way of doing things. We don't use this GL vertex calls anymore. And before we go, that another important thing is that the front faces of the triangles are determined by the counterclockwise order of vertices. If you have a triangle strip, it's difficult to have a counterclockwise order because this shared edge, as you can see, is on different sides, in different orientation for the neighboring triangles. For example, if you specify this as 0, 1, 2, the other will be 1, 2, 3, which is clockwise. We don't want that. We still want the front face here. Triangle strip automatically handles this. It just changes the order of the adjacent vertex for the next one. Its winding order means that the order always changes. Okay, so the next triangle is not 1, 2, 3. Actually, it's 2, 1. It's interpreted as a triangle as 2, 1, 3. And I talked about this graphic state. It's everything. There are global variables. The state variables change when you set the color to green. The entire vertex information will have the green color with them. And if you set the normal vector, all of the triangles will have this normal vector. But if you want a single vertex to have a different color and a different normal, you just change those global variables. So glColor3f changes the current color to this one. glNormal3f changes the current normal vector to this one. So whenever you call a glVertexT3f function to send something to the GPU, whatever the current normal vector is, it is associated with that vertex. So it's not, nothing is object-oriented here, because we don't have vertices and associated normals with them. There is no association, there is no object. So whenever you issue a draw command, whatever the current state is, that is associated. That's the attribute of the vertex. So that's bad for, that's a bad design, I think, for a graphics library like this, but it's very low level, and I think it gives more freedom to do certain things. And here, this example of calling glVertex to send geometry data over there is called the immediate mode. And you can imagine this immediate mode is very inefficient. When you make lots of glVertex calls, I mean, this part is very inefficient, but it's still really fast, right? I mean, I can still view the entire thing in real time. I'm drawing 180,000 triangles just for that tabletop, but it can still do it really fast. But it can do even faster. Okay, so if we didn't have this many glVertex call, one way to do is by using a functionality called vertex arrays. Vertex arrays are putting all that vertex data together in an array still on the CPU side. Okay, so so the vertex data is on the CPU side, but we can send that data to the GPU at every frame with just one function call. So we can replace these 180,000, actually it's 6 times 90,000. Okay, so there are 6 times 90,000, that many function calls. Instead of making that many function calls to send every vertex one by one to the GPU with these function calls, there is a method named glDrawArrays, in which you put your data on the CPU side in an array. And when you say glDrawArrays, and I'm drawing triangles, your data is in this array on the CPU, you can, that's what vertex array is. The data is on the CPU side, and you send, just like making function calls as glVertex3f, you make a single function call to send the entire data every frame to the GPU. This is still inefficient, as we imagine, because why don't we copy the entire vertex array data to the GPU? And that's called vertex buffer objects. So all these three things are explained very nicely. I'm going to give you a link to a tutorial. I think it was Songhu tutorial or Songho OpenGL. Yeah, OpenGL, GL vertex array, vertex buffer objects. His tutorials are really good. Yeah, this one, Songho. Now it's about vertex buffer objects. So vertex array. He also talks about vertex array. So these tutorials are really good. How it's, for example, in the immediate mode, he talks about in the immediate mode we have these vertex calls between glBegin and glEnd pairs. How this is inefficient for a triangle to draw a cube, and it shows, it's really interactive. It shows the vertices nicely in the correct order. This is how we would draw that cube. So with draw arrays, what we need to do, how do we initialize the draw arrays? So this is, let me also copy them in the chat box. This tutorial is really nice, and the vertex buffer object tutorial is better. Now the advantage of vertex buffer object to draw arrays, the vertex arrays, is that the data is no longer in CPU's memory. We don't need to send the vertex information at every frame to the GPU. We copy the data onto the GPU as a vertex buffer object once before we go into the while loop, and we just issue draw commands in our while loop. So this is the vertex buffer objects. So the vertex arrays, as I said, it's this pointer here. The data is still in the on the CPU. So we have the GL vertex pointer says that I have a data on the CPU side. I'm going to use it as to define triangles, vertices, for example. Each coordinate is a floating point number or an integer. And sometimes, as a programmer, we are responsible on how we are going to maintain our different types of data in memory, either interleaved or on separate arrays. So what I mean is that, for example, the vertices have several attributes. And in this spotlight example that I gave, a vertex has a normal information and a coordinate information. So these coordinate and normal values of a vertex can be on the same array in an interleaved fashion. Coordinate, normal, coordinate, normal, coordinate, normal. I can even put, if I want to color each vertex differently, I can also add color attribute to that vertices, and I can put everything on the same array in an interleaved manner in this way. For vertex 1, coordinate, vertex 1, normal, vertex 1, color, vertex 1 coordinate, vertex 2 coordinate, vertex 2 normal, vertex 2 color. It may go like that. So this stride tells the packing information of your data. Where do you get, by changing the stride from 0 to some other offset byte number, you tell that the next vertex value will be this many bytes after. So this actually, with this GL vertex pointer function call, you can tell OpenGL that I have my data in a packed format, interleaved format, and the vertex data is every 5 bytes there is a vertex, for example. You can tell that to OpenGL with this function call. You can also have different attributes. In modern OpenGL, actually the coordinates, so the vertex pointer by default contains coordinates in old OpenGL. And in order to use these vertex arrays, you need to enable the client state vertex array. And in modern OpenGL, what happens is that all those vertex attributes, normal, coordinate, color, they are just named generically. All of them are called attributes. Okay, so how you use those attributes is going to is the programmer's responsibility. So there is no actually GL vertex call is obsolete in the new OpenGL version. There is no vertices do not have coordinates. You're responsible to specify that this attribute is a geometric coordinate. This attribute is a normal vector. So therefore, to make it a generic attribute array function is this one. And as I said, these are just like API references. I'm not going to go over them in detail. And these tutorial links that I shared with you describe the vertex immediate mode, vertex arrays, and vertex buffer objects very nicely. And you can also use the example programs. The Spotlight C shows how you use vertex buffer objects in a program. And with the GL draw arrays command, you can send the vertex data to a GPU with just one function call instead of many GL vertex function calls. GL draw arrays will tell you, for example, I'm going to draw triangles. In your array, you can draw different parts of different objects in the single array. For example, in this draw array, I want to start from this index in the enable array, and I want to draw this many triangles. You specify where you're going to start in your data and how many triangles you are going to draw. The draw arrays use the vertex coordinates, get the vertex coordinates directly from your vertex data. If there are shared vertices between triangles, you need to put duplicate vertex information, because every 3 vertex is a triangle. So if there are some shared vertices, you need to duplicate them. You need to write them redundantly in your vertex data. But this glDrawElements mode is for the index version. We just say that I have my index information at some place in memory. I'm going to draw triangles. I'm going to draw this many triangles. And each index is an integer or an unsigned integer, whatever it is. You just specify type, as in C type. And then you give a pointer to the indices that are referring to those triangles. This is more efficient. You don't need to duplicate your vertex information with this drawElements function. Okay. So this one shows all of the data. Everything here is in the system memory. With every draw call, the vertex is copied. So every frame, we have this copying to the GPU memory. Now, the most efficient way, effective way to do this is to actually get rid of this every frame copying of these vertex data is use vertex buffer objects. And I mentioned this before. Actually, I also showed you how we create those things. So I'm skipping them quickly. We bind buffer. We send there are different buffers, array buffer or element array buffer. We can send the index. And with this buffer data function, we send the copy the data to the GPU. And after we copy our data, we can free our memory on the CPU side in RAM after the data is copied over there. We don't need them anymore on the CPU side. And after this point, after the data is copied over there, this glVertex pointer, just we did in vertex arrays, we can use this glVertex pointer again, but this time, this is no longer a pointer to memory. In the glVertex array functionality, this last parameter was treated as if it was a pointer. Now it's treated as a number. It's treated as an offset. So that's really interesting because the same function sometimes is used for both vertex arrays and vertex buffer objects. So how does it know whether we are currently using vertex buffer object or not? By looking at that glBind buffer. Okay, if currently there's a buffer bound and we are using a vertex buffer object, this pointer is no longer going to be treated a pointer to somewhere in CPU side on the memory. It will be treated as an offset. Okay, now we are going to be sending null value, 0. For example, if you're going to start your drawing a vertex pointer at the beginning of your data, you just write 0 here. Okay. Same with drawElements. Again, we need to enable the client state, whether we are going to have vertex information as an array, color information as an array. So this is where we can enable and disable them, and just we draw them with. Yeah, this is what I already told. This glVertex pointer and drawElements, the last parameter is sometimes treated as a pointer to somewhere in memory and sometimes as an offset. So if you're using vertex buffer objects, it becomes an offset. If you're using vertex arrays, it becomes a pointer to some array in memory. And OpenGL makes this decision as follows. If a non-zero name is, if you're using buffer objects, the last parameter is treated as an offset. Okay, in both cases. Now, if you look at the performance comparison, when we drove an armadillo model composed of 200,000 triangles, resulting in a total of close to 1 million triangles, the vertex buffer object with the frame rate is around 100 frames per second. If we just use vertex arrays, okay, which means that if the data is copied over to the GPU at every frame, it drops to 20 frames per second. Okay, so vertex buffer object is the most modern and more efficient way of drawing these things. And finally, the transformations. These are TranslateF, RotateF, ScaleF. The parameters are like this. The TranslateF function these are the translation parameters, scale parameters. Rotation is a little bit different. it's rotate around an axis that passed through origin. It's not really an arbitrary axis. We specify the angle. When we say glRotatef some angle, you remember in our basic rotation in 2D, we always rotate around origin, right? In three-dimensional rotation, the origin, I mean, are we going to rotate around the XY plane, XZ plane? It's not specified. So how OpenGL implements this is, this axis is actually like a vector. It's a point, and you can consider this as a point, and it defines a vector that passes through origin. So one end of this arbitrary axis is always 0, 0, 0. The other end is this axis x, axis y, and axis z. So OpenGL gives you an arbitrary rotation, but it's not that arbitrary. Your rotation axis that you rotate around is an axis that passes through origin, And the angle is in degrees. Unlike the cosine and sine functions in C, which is in radians, here RotateF gets the parameter in degrees. So a good question, what happens when the GPU memory is full? I think it should give an error, and maybe not all of the data is copied at that point. I have never come across in a case where the GPU memory was full, but it may be full when you're drawing all those triangles. And how in the C side, when we're programming on C, we usually check this whether our malloc or the other memory allocation functions return null to us in terms when it's full. There should be a mechanism to check the buffer data function. It should return the state, current state. For example, if the buffer data returns some certain state, we can actually take a look at that. Maybe it is written there, GL buffer data. GL buffer data, memory full, memory, yeah, out of memory. Actually, people have asked that, out of memory. So it should return something. Actually, it returns an error. So GL out of memory. So when this buffer data, it returns an error. So and how do we get this? So if malloc returns null in our case, but the OpenGL, the GPU, this is about the GPU side. So how we get this error, I'm not sure about that. But since not every resource is unlimited, it may get full, and it should notify the developer or the user, the client side, in some way. Okay, and transformations apply in reverse order means that actually you shouldn't memorize it like this. What happens is that when we are going to draw a cube, imagine the current model view, the current mode is model view matrix. Imagine we load it with load identity here. All these function calls, what they do is they create a matrix and they right multiply themselves with the current matrix. What happens is that this glScale becomes the rightmost matrix that is multiplied with the model view matrix. So when you try to draw something, drawing a cube is just like specifying its vertices. And when we specify that vertices and also multiply it to the right, what will happen is that the last transformation that we have applied is actually effectively is applied on the vertices first. So this cube is first scaled, then rotated, then translated. Okay, so when you're writing your code, you should keep that in mind. All the code you write here is actually doing some matrix multiplication. You're composing a composite transformation by multiplying these matrices from left to right. Yeah, this is also I talked about. All the transformation affect the current matrix. Also, the final thing is the camera position. There is no camera position specified, but there's a good function. This gluLookAt function that I mentioned is a really nice utility function, which takes 3 parameters. I'm going to talk about that last, and since we're out of time, I will stop here. But you should be able to understand. You should just try to inspect this, the inside of this while loop, I'm going to actually share the spotlight.c, the modified version, the glFW version with you. So you can go inside this while loop and see what is going on. For example, what does this GL you look at doing? How do we rotate our camera on a circle? Here, the camera XYZ, it has a position. And if you look at this camera XYZ position, what does it look like? It looks like the circle equation, right? So I convert certain things, this cosine, radius times cosine, minus, so this is actually, it says in a specific height. So it's actually this X and Z coordinates, they define a circle on the XZ plane. And when the circle is at some specific height, that circle becomes parallel to the XZ plane. And I just specify my camera is here. This is the camera position. This is where it is looking at. My camera is looking at origin. It's always looking at 0, 0, 0 at a fixed position. And its up vector, the last three parameters are the up vector, which means that I'm looking at a, well, let me show you. I don't have any objects with me. So it's like this. So my camera is looking like this, but I specify the up vector to be always 0, 1, 0. As you can see, they're not in 90-degree angle. They're not orthogonal to each other. Just like I think in assignment 2, it was also like that. We need to correct the up vector to be like this. And how do we do that? We first cross product these looking directions. So we are looking at from camera position to 0, 0, 0, and this is my up vector. I cross product these two first to find the z-axis, which is towards you, like this, or yeah, not the z, sorry, x-axis, because your looking direction is z. So z and this is not the correct y. And after I find this x-axis, I cross product these two together once more to correct the orthogonal up vector like this. So the good thing in GL, you look at this, you don't need to specify the up vector as orthogonal to your looking direction. So it's very convenient for the user. So having 0, 1, 0 means that your camera is going to, your image is going to appear like this. It may, these tilting, you're not tilting your camera in this direction. You're doing the tilting in this direction. You look at my face. I mean, if you see it like this on the image, my face is rotating if you just think about from the image's perspective. But when I do this, my face is still straight up on the image. Yeah, and exactly. And this GL you look at, it just multiplies the current model view, not P, current model view matrix. It updates not the projection, because P is, so let me correct it here. It updates the MV matrix only, because P is not combined yet. Okay, P is the GL you look at creates transformation, the camera transformation we have talked about in class, translate and do the rotation. It creates that matrix and multiplies the current model view matrix with that. All right. So, and this is just I can actually replace this GL you look at with some GL rotate and glTranslate code. Okay, so yeah, so this will be first translated and rotated. So with some glRotate and translate function calls, you can actually implement your own GL you look at functionality. All right, so that's it from me for today. We are going to continue with this and finish it on Monday, but I think you should have the necessary sufficient information right now to start working on the assignment, and it shouldn't take too long. As I said, you're going to be using OpenGL, existing functionalities, default lighting, default color. You will not be writing any programmable shaders, so you should be able to do that. But if you have any problems about the assignment, please let us know. All right. Thanks, everyone. See you all on Monday. Have a nice weekend. Bye-bye.